Hidden beneath a quiet, windswept field in Suffolk, England, lies a secret that is invisible to the human eye standing on the ground. From the surface, you see only uniform rows of crops, but climb several hundred kilometers into space aboard a satellite passing overhead and look down through the lens of a multispectral sensor. Suddenly, a spectral phantom emerges, traced in shades of infrared reflectance. The crop canopy reveals geometric anomalies. Where ancient stone walls lie buried beneath the soil, the crop growth is stunted, turning pale red under the near-infrared spectrum. Where ancient ditches once held water, the crops thrive, glowing bright with chlorophyll. This is a crop mark, a physical memory of human history preserved by the soil and read by a sentinel in space. Why has Earth's space-based technology become the ultimate sanctuary for our fragile natural and cultural past? And how are orbital sensors rewriting our understanding of what lies beneath? This premium documentary reveals how Earth system science and remote sensing are transforming heritage conservation. We will journey across continents, from Venice's sinking waterways to the biodiverse rainforests of Costa Rica, discovering how satellite arrays like Sentinel, Landsat, and GEDI work in harmony to monitor risks in real time. You will understand the physics of radar interferometry, the biogeochemistry of vegetation indices, and the collaborative data networks used by global organizations to shield Earth's natural memory. By the end of this film, you will see how everything on our planet, from deep-water ocean floors to high-altitude mountain sanctuaries, is connected by a single digital shield designed to protect our shared legacy for generations to come. The history of humanity is written across Earth's fragile surface. Today, our monuments face a double-edged sword of destruction: climate change and intense land use. Global air temperatures have risen by more than 3/4 of a degree Celsius since the Industrial Revolution, amplifying environmental threats. Fluctuating groundwater, wind erosion, and atmospheric pollution are risk multipliers that slowly erode delicate historic citadels. Until recently, monitoring relied primarily on visual surveys. But today, the Copernicus Earth Observation Program stands as one of the world's most powerful space-based environmental monitoring systems, delivering vast quantities of openly accessible satellite data. Through its land and climate services, scientists continuously monitor planetary risks and environmental change. Venice, Italy, wages a quiet war against subsidence. This struggle is monitored with millimetric precision by Copernicus Sentinel-1. Using active C-band synthetic aperture radar, Sentinel-1 scans Venice day and night. By comparing repeated satellite passes, geophysicists use persistent scatterer interferometry to measure subtle ground motion. If an historic palazzo sinks by even a single millimeter, the radar signal changes just enough to produce a measurable phase shift. These deformation maps are updated every few days, allowing engineers to detect structural instability long before visible cracks appear. Optical satellites exploit the biology of crops to map buried ruins. Satellites such as Sentinel-2 calculate the Normalized Difference Vegetation Index, or NDVI, by comparing red and near-infrared light reflected from vegetation. When crops grow above buried Roman roads, underground stone restricts root growth and moisture availability. The stressed vegetation reflects less near-infrared light, producing lower NDVI values and revealing pale crop marks. Meanwhile, crops growing above buried ditches benefit from greater soil moisture and richer organic material. They flourish, producing higher NDVI values that appear brighter from space. Without disturbing a single stone, satellites can reveal forgotten settlements hidden beneath modern farmland. To promote satellite-based heritage monitoring, the European Commission established the Copernicus Cultural Heritage Task Force, known as CCHTF. Coordinated by Italy's Ministry of Culture, the initiative connected Earth observation scientists with archaeologists, conservation experts, and heritage managers across Europe. By collecting expert recommendations, the task force transformed dozens of user requirements into practical technical solutions. Rather than creating an entirely new satellite service, the group recommended developing a unified online platform capable of delivering customized Copernicus products directly to heritage professionals. Natural heritage protection also depends upon sophisticated spatial information. Under the Convention on Biological Diversity, nations commit to protecting native ecosystems and species. To support this mission, the United Nations Development Programme and the United Nations Environment Programme created the UN Biodiversity Lab, providing access to more than 100 global environmental datasets. One flagship project is the Map of Hope, which identifies essential life support areas throughout countries such as Costa Rica and Colombia. By combining satellite information with local ecological expertise, governments can identify landscapes where conservation simultaneously protects biodiversity and secures freshwater resources. Many conservation decisions rely upon the IUCN Red List of Threatened Species, the world's leading database on extinction risk. However, integrating species distribution maps into geographic information systems requires careful protection. For animals vulnerable to illegal hunting or wildlife trafficking, precise locations are intentionally concealed. Public maps display generalized distributions, while exact coordinates remain restricted to authorized researchers. This balance allows conservation science to remain transparent, while ensuring sensitive ecological information does not become a tool for exploitation. Forests contain most of Earth's terrestrial biodiversity, while regulating fresh water supplies and storing enormous quantities of carbon. Yet millions of hectares of primary tropical forest disappear every year, accelerating climate change. To fully understand forest health, scientists need more than satellite photographs. They need three-dimensional measurements. GEDI, mounted aboard the International Space Station, uses laser pulses to measure forest height, canopy density, understory structure, and biomass. These detailed vertical profiles help scientists estimate carbon storage, validate climate models, and strengthen international conservation efforts. Monitoring Earth's water systems remains surprisingly fragmented. Different satellite services often manage lakes, coastal waters, rivers, floods, and oceans independently, limiting scientists' ability to understand complete watersheds. To address this challenge, the Water Force Consortium proposed a roadmap for integrating water observations across the entire hydrological cycle. One major objective involves expanding automated stations and synchronizing ground measurements with satellite observations to improve calibration and reduce uncertainty in global drought monitoring. Protecting Earth's memory requires more than technology. It demands collaboration between archaeologists, ecologists, climatologists, engineers, and local communities. For thousands of years, humans adapted crops such as olives and wheat to survive harsh climates. Ancient settlements remain physically embedded within these living ecosystems. Radar satellites monitor slow tectonic movement. Vegetation indices reveal buried archaeological structures. Laser scanners measure forest architecture. Together, these complementary technologies form a digital archive that helps governments and communities preserve both cultural heritage and natural ecosystems before they disappear. The future of Earth observation is only beginning. Next-generation Sentinel missions will introduce even more advanced sensors capable of measuring thermal radiation, hyperspectral signatures, and subtle environmental changes with unprecedented precision. Future concepts, such as dedicated aquatic monitoring satellites, promise to close critical observational gaps while supporting machine learning systems capable of forecasting environmental change more accurately than ever before. What began as humanity's desire to better understand the landscape has evolved into a global digital shield. From buried civilizations beneath quiet fields to towering rainforests, from sinking cities to the vast oceans, satellites are quietly watching over our planet, not as silent observers, but as guardians of Earth's shared memory, helping preserve the story of our world for generations yet to come.